Let me start by saying that it's a great honor to be able to give this talk here in this very special meeting. For those of you that don't know me, my name is Eloy de Lera Acedo. I'm an associate professor of radio astronomy at the Cavendish Laboratory. So my office is at the Babcock Center, which is just across the grass there. For those that know me, I have to apologize because probably you will have seen a lot of the slides that I'm going to present today, so you will have to bear with me for the next half an hour. What I would like to talk to you about today is my take on how the world of radio astronomy is going to look like the next 50 years. And I say the next 50 years, not directly related to the last 50 years. We are celebrating with this birthday conference for the IOA, but because some of the main observatories in the making, radio observatories, have a lifespan of about 50 years. I'm planning to retire a bit later than 2038, but still I won't be able to see during my working lifetime the end of SKA, not even the Habitable Worlds Observatory in the making. Huh. That was working.
Try again. No.
There you go. So let me start by explaining what am I going to talk about. What is radio astronomy in this context? I'm going to be talking about doing astronomy at meter and centimeter wavelengths. So in this very well-known picture of the galaxy at multiple wavelengths, is it better to use this? Yeah. At multiple wavelengths, what I will be talking about is how we'll be doing astronomy for the next 50 years at meter and centimeter wavelengths, so the top of this diagram. And this is the overview of the talk. I will start by describing the radio telescopes of the future. What are the enabling technologies? What are the radio telescopes that are being planned or in operation that are shaping how we do radio astronomy, and will continue to do that for the next few decades. Then I will move on to talk about the science goals that these radio telescopes will be tackling, and I will end up by talking about what we are doing in Cavendish radio astronomy today and for the foreseeable future. Right, so let's start by talking about the enabling technologies. What are those technologies that are making possible better radio observations in the present and towards the future in the next few decades? The first one must certainly be big data technology. Advances and developments in big data, GPUs, but also not only the hardware, but all the software and memory and storage, data storage associated with the developments of big data in many other industries is enabling us to do better radio observations. We're going to be able to do things like archiving 300 petabytes of data with the SKA every year and running the science data processor in 135 petaflop computers. The other enabling technology that is key in current radio telescopes and in the future is low-cost, ultra-fast digital front ends. Something that has always been an enabler for better radio observations is definitely key at present. The ability to do things like wideband analog to digital converters, allowing us to digitalize things in real-time spectrometers, is certainly providing capabilities that we didn't have until relatively recently. And of course, the last one is related to fabrication. Radio telescopes are big things, so they can be expensive very quickly. We want a lot of effective area, and the new radio telescopes and radio observatories, as you will see in a moment, are very large machines with many collecting elements, each of them. So the ability to make these cost-effective is crucial. Advances in manufacturing technology are allowing us to do this. So, how does the radio telescope of the future look like? The radio telescope of the future is an all-digital system from the antenna down. So we are developing systems where we're digitalizing the signal as soon as we can in the receiving chain, allowing us to do fast processing and be able to do things like better calibration. It's an all-sky system, being able to look at all directions in the sky, in many cases without mechanically moving our telescope, and also it's a very wideband system, from DC to daylight almost, although that will defy the definition of radio that I said before. They are big. Sensitivity is key. If you really have to say one thing about telescopes like the SKJ is that they are very large. Not necessarily reinventing technology that we already know that works, but they have a lot of collecting area, therefore a lot of sensitivity. And they are data machines, which really can mean many things, but in this context, what it means is that they will be ready to enable multi-messenger, multi-probe astronomy, combining the data products, combining the output of these, the radio observations they will do with many other probes, many other types of observations of the sky. Right, so before I go on and talk about the two main radio observatories in the making, the SKJ and the next generation VLA, I would like to make two mentions of radio telescopes that currently and for the future are really making the difference. The first one is CHIME in Canada, which most of you will know, is the telescope that has discovered the most fast radio bursts. So it's really opening a window to the transient sky, to the transient radio sky, a very well-designed instrument that is definitely the reference in the field. And the other one, which we have heard about in this conference a few times, is of course the Event Horizon Telescope with its imaging capabilities, unveiling a lot of the mysteries around the physics of black holes. SKJ Observatory. So the SKJ is actually two instruments. There are two SKJs, one in South Africa and one in Western Australia. The one in South Africa will be made of dishes like this one. It will be dishes that will be added to the existing Meerkat radio telescope with baselines up to 150 kilometers. The one in Western Australia, a lower frequency instrument, will be an aperture array. So it will have 512 of these phased array stations, each phased array with 256 dipole elements closely packed together. And as I said before, if there's one thing we can say about the SKJ is that it's going to be big, it's going to have a lot of collecting area compared with current instruments. I think Leon mentioned this morning 8 times the collecting area of LOFAR. So that's about the improvement, and you can see here how that sensitivity is going to grow from now, where we are building already the first stations of SKJ. The first 4 stations are being constructed as we speak, all the way to the beginning of scientific observations, both for the mid-frequency band, so the array of dishes in South Africa, and the array of the instrument with aperture arrays in Australia, the SKJ low. So you will see when we are likely gonna surpass the sensitivity of some of the most sensitive instruments today. And here on the left of this slide, on the right of the slide, you can see the frequency bands that will be covered with the baseline design, 1, and with potential upgrades of the baseline design, 2. It's worth mentioning that the UK has a leading role in the SKJ. We are one of the 3 host countries, together with South Africa and Australia, where the instruments are going to be. SKJ headquarters are hosted in the UK at Jodrell Bank Observatory. And the UK is also the largest cash contributor to the project. Additionally, UK has led and continue to lead a lot of the working packages that have developed things like the Science Data Processor, which has been mostly led from here, from Cambridge. So let's look at the timeline for SKJ. I think you probably could infer a bit of it from the diagram I saw before, but we are looking at the first 4 stations by the end of this year, for low, next year for the mid array. But as you can see very quickly, the number of stations is going to grow with an expected release of early data, release of data for the AA2 system, so around the end of 26, 27, depending on which of the 2 instruments, and a potential first light around 2028, 2029. The other major radio observatory, in this case one that is mostly going to happen in the US, is the next generation VLA, an upgrade to the VLA. This will look a little bit different from SKJ because it's going to be a dish array. In principle, there's no plan for the low frequency aperture arrays like in SKJ. It's going to have 214 18-meter antennas, giving it an order of magnitude improvement in sensitivity, but also in resolution with respect to JBLA. And it will cover a fairly large frequency range, which is maybe the thing that is worth mentioning here. NGVLA will be the bridge between SKA and ALMA. So it's going to cover those intermediate frequencies, basically providing a continuous coverage of the entire spectrum from 50 megahertz, which is the lowest frequency of SKA, all the way to almost 1 terahertz. And this is the timeline for NGVLA. Might be a bit outdated now. I'm not 100% sure, although just last year they unveiled their first prototype, so maybe it's not too far from this. But as you can see, they are expecting to be building the telescope for the next, the best of the next decade, achieving full operations by mid-next decade. Right. So to conclude with this section, what comes after SKA and NGVLA? Leon as well this morning mentioned this in the context of 21-centimeter cosmology, which is the main driver for the science of radio astronomy beyond Earth. There are several projects developing arrays, developing single antennas to be both in the surface, on the surface and in orbit of the moon in space. So a real era of radio astronomy from space, trying to exploit some of the special conditions of the moon, like low radio frequency interference for now, no ionosphere, and a few other benefits. And as I said, we have a plethora of projects in the making by the usual space agencies. Okay, let's move on to talk about science goals. So I seamlessly stole this from the SKA website, but I just wanted to give you an overview of the different science goals that are going to be driving radio observations for the next few decades. We could classify these in different ways. I just chose to classify them according to the type of observations or the observable that we are going to be looking at. For example, the probe of the cosmic dawn via the 21-centimeter line at high redshift, or the studies of cosmology and dark energy via observations of the 21-centimeter line at lower redshift, as well as the exploration of galaxy evolution. All of these three cases really mainly rely on observations of gas radio emissions, observations from hydrogen. We also have science goals that depend on the direct imaging capabilities of a telescope like SKA, both studies of our own galaxy, the sun, or even planets in the Milky Way will be using this imaging and capability and high sensitivity of telescopes like the SKA, radio telescopes like the SKA. We will also be able to learn a lot about magnetic fields in space, and this is mostly thanks to the polarization capabilities of instruments like the SKA, measuring the magnetic fields and the polarization rotation in the ISM and in the IGM via observations of long-distant objects. And finally, something I referred to before, which is a new window that is being opened now, is the observation of the transient sky, the radio transient sky, and our ability to then inform things like relativity or completely new things like fast radio bursts. The SKA will be informing or will be doing studies of relativity via pulsar timing, aiming to observe most of the pulsars in the Milky Way. Very good. So this will take me to the end of the presentation. I want to talk a little bit about what are we busy with at Cavendish Radio Astronomy today. I could talk a lot about the lustrous and long history of radio astronomy at the Cavendish, but that's not what I'm here to do or what I want to do. My job is to talk about today and the future. So I will go straight into what are the projects we are busy with at the moment, what are the projects we are going to be busy with over the next decades. And as you can see, our work mostly revolves around the square kilometer array. and specifically the SKJ low instrument, with a few other projects like single antenna radiometers, interferometers, and even a space mission to study the 21-centimeter line at high redshift. That's what our main focus is nowadays. I think I'm going to skip a lot of this because Leon already introduced the 21-centimeter line, maybe just to stress that the challenge is an enormous observational challenge. The challenge is that the cosmological signal, the 21-centimeter line, the fluctuations of the 21-centimeter radiation or spin temperature radiation around the CMB are expected to be several orders of magnitude below the foregrounds, even though the foregrounds are expected to be smoother. But the biggest issue is not that. The biggest issue is the instrument-induced power, either generated by the radio telescope itself or mixed from the foregrounds and other sources of power, but creating spectral structure that is, again, several orders of magnitude above the cosmological signal. Calibrating your instrument to get rid of that, and also obviously the foregrounds, is the challenge here, and a lot of us have been at it for quite a while now, but improving, as we saw from Leon this morning. So the hand for the 21-centimeter line, again, I think we saw most of it this morning. We have the sky average global signal, average across all directions of the sky. In this plot, you have the envelope of theoretical models as predicted by the simulations by Anastasia and her group. Those are in the blue area, and in gray are those that include some exotic physics that could explain some of the observations, like the edges observations that were reported in 2018. And at the bottom, you have the results for the power spectrum measurements by radio interferometers, providing upper limits, as you can see, coming down with time, still about maybe an order of magnitude or so from the standard models. So we have, as references in the field, the EDGES 2018 detection, the SARAS-3 non-detection that was ruling edges to a good degree, ruling out edges to a good degree, and then the power spectrum upper limits from mostly 3 interferometers, HERA, LOFAR, and MWA. And what have we been able to do with these upper limits and observations and non-detections? Well, we are able to start constraining astrophysics of the early universe, of the time when we were going from simple cosmology to hard and complicated astrophysics. This is work that has been done by members of the Kepler Institute of Cosmology here in Cambridge, part of the group from Anastasia Fialkov here at the IOA and of my group at the Cavendish, so this is collaborative work. We are starting to constrain the shape of the cooling and heating of the intergalactic medium during this transition, during the cosmic dawn. The reference of this black dashed line is adiabatic cooling in the early universe when we are plotting the spin temperature over the background temperature, combining observations from HERA, the HERA radio interferometer, and the SARAS single antenna radiometer global signal. As you can see, we can start to define that shape of the initial cooling and later heating of the intergalactic medium, which also allows us to talk about things like the radio emission and the X-ray luminosity of the early galaxies. This is work from one of the Kepler fellows, Harry Bevins, who was putting constraints on how radioluminous and X-ray luminous were the early galaxies, showing that, well, still not super tight constraints, but defining how the early galaxies were probably fairly good X-ray hitters, but maybe not as much radio emitters. Of course, this is still a very large parameter space that needs a lot of constraining. Good, so let me move on, I think in the interest of time, since we have 5 more minutes. Rich, though we don't have 5 more minutes? You just told me? 5, excellent, very good. Good. So REACH is the single antenna radiometer that is keeping us busy in Cavendish radio astronomy. It's in South Africa. It's trying to detect the 21 centimeter signal, the global sky average 21 centimeter signal. We started about 5 years ago developing REACH, even before EDGES published their potential detection, asking ourselves a question. How can we convince ourselves and everyone of a detection given the difficulty of getting rid or dealing with the systematics in this type of instruments? So we come up with a proposal and a solution that we are now implementing and already using. First, we will use a multiple concurrent system, multiple different radiometers with different antenna designs, observing the sky simultaneously, which helps a lot with trying to distinguish what is a systematic erasing from the instrument, what is coming from the sky. A very advanced joint Bayesian analysis where we are fitting physically motivated models of the three main parameter spaces, the foreground, the 21 centimeter signal, and the instrument. Again, with the quest of being able to explain and convince ourselves that we have made a detection and that we are not mixing foreground things with systematic things and so on. Continuous on-site radiometer calibration, so we are constantly doing the calibration of the receiver and improving it all the time. And this is already part of our data coming from site. So we started observations in January. This is not looking at the sky, so this is very important. This is just talking about the receiver calibration, which is one of the first things one needs to deal with, but I want to show you basically the latest things we have managed to get from the system on site. So if instead of looking at the antenna and the sky, we connect a 50 ohm load and use our Dickey switch radiometer, and we try to calibrate the temperature, the thermal radiation from a resistor, which should be flat across frequency with the Dickey switch radiometer. This is what we are getting at the moment, which is relatively flat, fairly flat for what we need to do. Just to put things in context, this will be the EDGES signal for reference. So I think the message here is that we should continue doing the good work we are doing, making sure that when we connect the antenna, we can keep the calibration to these levels, also improve these things, because then we might be able to see if the EDGES signal is there or not, or if there is something else. 2-3 minutes, something like that. 3, very good. This is actually with the antenna connected now. So this is the waterfall plot, frequency versus time, where you can see at the end of the observation, we have the galaxy overhead, but it also shows you some of the challenges with instruments on Earth, which are things like radio frequency interference, FM channels, satellites. The good news is that it looks fairly clean for the most part, especially at night. So when the local radio communications stop, when planes stop flying over, plane communications stop, the spectrum looks very clean. We are very pleased that it's like that, because I think this is going to make things easier for us. The other thing we are very busy with is developing SKJ. We have been leading the development of the low radio antenna and low noise amplifiers, the science data processor, as I mentioned before, and we are very busy now with developing data pipelines for the 21 centimeter analysis at high redshift, as well as the development of the science regional center that will be in the UK to facilitate data to the community. Okay, the last thing in terms of big projects we are busy with is radio astronomy from the moon, from the far side, looking at the dark ages. As I said, there are satellites, single antenna radiometers, both in the surface and in orbit. We are working on a small satellite that will be in moon's orbit, observing from the far side of the moon, shielded from the Earth, trying to get to that 21 centimeter signal from the dark ages in a few years from now. So I will have to skip some of these details. Come and ask me if you're interested. We are in the middle phase developing technology for this satellite at the moment. This is funded by the UK Space Agency, and we are hoping for a 2-year mission by the end of this decade or earlier. brief mention about the Molar Radio Astronomy Observatory. It's still operating. It's only 5 miles south of Cambridge, and the future for it looks more or less like this. We still have our Amy array with a new life dedicated to the study of transients and radio transients in the sky. We are using it to develop technology for the SKJ, and we are also using it for 21 centimeter experiments, both test of array technology, but also single antenna experiments. And if you want to visit our labs, just let me know. I'll be happy to take you across to the Badcock building and show you what we are busy doing. And to conclude, the final slide is to say that looking into the future, what we are doing in the Cavendish Radio Astronomy is also to collaborate a lot with people in the Institute of Astronomy. So these are two of our main collaborators in the Institute of Astronomy, where we are doing a lot of work together, either in existing instruments and observations or planning and developing things for the SKJ and for the future. And I think I will leave you with those conclusions. Looking bright, second golden age, and we have a lot of things to do here in Cambridge, especially if we put together our strengths and skills from the 3 departments. At the moment, 21 centimeter radio cosmology is our forte at the Cavendish. Happy birthday, IOA.